Okay, now we're finally to particle bound to a sphere. And so I'm going to introduce some Cartesian coordinates. I know we talked about those in class, but I'm going to do it again here. And I want to emphasize that r is constant. All right, so I have a ball of some sort. And I want to know what's the, where's the electron when it's bound to that ball or bound to that sphere, and what is its energy? So what I'm going to do is I'm going to explain spherical coordinates, and then I'm going to take you through the Laplacian and the Legendrian in order to get you to what are called the Legendre polynomials and introduce this idea of the spherical harmonic. Lots of words. I will put meaning to these words. So if you're reading ahead before you're watching the video, this is going to be helpful. Okay, so first of all, psi of x, y, and z. So three-dimensional, you've got x coordinate, you got y coordinate, you've got z coordinate. We are going to convert that into wave function as a function of r, theta, and phi, where theta is your colatitude. So theta equals colatitude angle, and phi equals azimuthal. There's an I. Oops, azimuthal angle. All right. And so the best way that I know how to explain this is to go into the corner, and I encourage you all to do this. Next, I'm going to turn. All right, my microphone has now been switched over. I encourage you all to do this. Go to a corner and back yourself up into a corner. Put your hand up, so your hand is R. Put your hand up, okay, in the corner, but stay along one wall. Okay, your hand is R. You've come down by theta, and you've come over by phi. Okay, so there's some plane here that you're representing with respect to phi. Okay, this is theta, this is phi. So your hand can be anywhere, and you can represent that as r, theta, and phi. Okay, go team. I encourage you all to do this. It really does help. Okay. Hopefully the microphone is back on. All right. So those are the spherical coordinate system, and our Hamiltonian, which for x, y, and z is going to be minus h bar squared over 2m partial squared partial x squared plus partial squared partial y squared plus partial squared partial z squared plus whatever our potential energy is in the x, y, and z coordinate system. Okay, so this is known as the, well, we call this del, but it's also known as the Laplacian. And this is what we're going to have to convert to spherical coordinates. Why am I showing you all of this? I'm about to put a lot of math on the board, and you're going to be overwhelmed when you're reading Atkins going, do I need to know all of this math? No, you don't. Yeah, that's a lie. Yes, you do. But you need to respect where it comes from and know what it means and how to read it. But in terms of using it, we're going to jump to the answer. But I want you to have an appreciation for what it represents. Okay, so the Laplacian represented is this del is equal to the derivative portion of the x, y, and z, so second derivative. I'm going to now convert that into spherical coordinates. Okay, and I'm going to just, no, I'll go ahead and explain as I write it out. So del squared equals, del squared equals partial squared partial r squared plus 2 over r partial r plus 1 over r squared sine squared theta d squared d phi squared. Oh, those should be partials. I'm sorry. So partial squared partial phi squared plus 1 over r squared sine theta partial theta sine theta d theta. I'm going to pause and make sure I got that right. Yes, I did. Go team. Okay. And so the cool thing is I can take out this 1 over r squared and 1 over r squared, And I can amazingly enough, I can simplify this. So I'm going to get del squared equals, again, so I'm going to pull some stuff out. So I got partial squared, partial r squared. So that's just that first term, plus 2 over r, partial r, plus 1 over r squared, lambda squared. There's a big lambda here, okay? And this big lambda, I'm gonna erase some stuff. Okay, so big lambda squared equals 1 over sine squared theta, partial squared, partial phi squared. Yeah, this part. Plus 1 over sine theta d theta sine theta d theta. Okay, cool. This whole thing is known as the Legendrian. Legendrian. All right. And it seems intimidating because when you're reading in Atkins, you're like, well, that's weird. So I'm just showing the simplification, and this is section 7F.2 on page 285. All right. What does this do for us? Well, let me show you how it simplifies the Schrodinger equation. Are you going to be solving any of this stuff? No, I don't think so. If you are, it's going to be simple stuff. All right. So I've got h psi of r, theta, and phi, keeping in mind that r is constant. Okay, r has to be constant in all of this. R is not going to be constant when we apply this to the hydrogen atom. We'll get to that in a little bit. So h Hamiltonian operating on psi as a function of r, theta, and phi is equal to e psi as a function of r, theta, and phi. Okay, and again, r is a constant. Okay, so our Schrodinger equation, when you convert this to spherical coordinates, becomes minus h bar squared over 2m del squared psi of theta and phi, because del squared contains within it r. Okay, and this is equal to e psi of theta and phi. So I've taken out now the r component of the wave function. And I can simplify this even further by saying that this is the same thing as minus h bar squared over 2m 1 over r squared lambda squared, the Legendrian, psi theta phi is equal to e psi theta and phi. Allison, why do we care about all of this stuff? I'm showing you. This is the cool part. Okay, this is what we call separation of variables. I've been able to separate out the variable of r into these other parts because they're constant. Hence the reason why r is constant is so important for this particular model. Again, the model is particle bound to a sphere. So because r is constant, it can go into the operator as well as be incorporated into the energy in the eigenvalue. Which is it? It is not. Well, actually, no, it is. Yeah, it is. It's in the moment of inertia. Okay, so using the separation of variables, we can continue on and separate out our phi and our theta. So again, theta, that's what comes down. Phi is what comes over. So this psi of theta and phi is going to equal two functions multiplied by each other. And aptly named big theta as a function of theta multiplied by big phi as a function of phi. We like to keep things simple. Okay, so this is called separation of variables. And this separation of variables allows us to independently solve the Schrodinger equation for each of these wave functions. Okay, so we have the wave function of theta and we have the wave function for phi in the two different directions, or with respect to the two different angles, the theta angle and then the phi angle. Okay, go team. So what we're going to do is we're going to solve the Schrodinger equation with just theta, and we're going to get a wave function, and we're going to solve and determine what the wave function is likewise for phi, and then we're going to have an energy for theta and an energy for phi. Cool? Okay, pause. All right, welcome back. We are going to now have our our theta wave function, and that is equal to a constant A times a function P L m sub L as a function of cosine theta. All right, where L equals 0, 1, 2, and so on, and m sub L equals minus L, 0, to positive L. Okay, so first of all, let me talk about what this notation represents. P sub L, P with subscript L and superscript m sub L as a function of cosine theta. This is what's called a Legendre polynomial. So P L m sub L cosine theta equals a Legendre polynomial. And just like with the Hermite polynomials, the Legendre polynomials are going to be these functions, which actually they don't give you any Legendre polynomials. No, pause, I'll go find some. Okay, back again. Okay, so the Legendre polynomial is typically written something like this. So I'm going to say n is 0, 1, or 2. And Pn of x is equal to 1x and 1/2 3x squared minus 1. Okay, so the way that our Legendre polynomials work is our x is cosine theta. And so in this case, for it would be L equals 0. So this is the example. Actually, so here's the table. And here's our example. So for L, we would have 0. So P sub L of cosine theta is still equal 1. Okay, but for 1, L equals 1, P sub L of x is equal to x, but our x is cosine theta. Okay, and for L equals 2, we would have 1/2 3 cosine squared theta minus 1. Okay, so everywhere you see this x in the Legendre polynomials tables, we actually put a cosine theta because cosine theta is our x. Sound good? And you'll see this form, 3 cosine squared theta minus 1. You'll see that function in the next part that we're going to get to. But that's where the origin of where that particular portion comes from. Specifically, it's from the theta piece because that's what carries the Legendre polynomial. Cool? Okay. Most of me on these few videos is just explaining some of the mathematics such that when you read through it, it actually kind of makes sense. And it's not just a bunch of equations all at once. I'm showing you the pieces, where all the pieces come from. So when you see the puzzle pieces together, there's a little bit more coherence between them. Okay, so L is restricted to 0, 1, 2, and so on. And there are 2L plus 1 different wave functions here. So there are 2L plus 1 different wave functions contained here. And this is where the m sub L will tell you which specific wave function you've got. So minus L up to 0 to positive L. So that's where the 2L comes from, plus 0 here. Or plus 1 is this 0. So if L equals 3, m sub L equals minus 3, minus 2, minus 1, 0, 1, positive 1, positive 2, and positive 3. And so if L equals 3, the angular momentum equals 3, I then have 2L, 6, so the number of wave functions equals 6 plus 1, 1, 2, 3, 4, 5, 6, 7. There are 7 m sub L's. Okay, so there are 7 possible wave functions from this combination of L equals 3 and m sub L. Okay, oh, by the way, for every wave function that yields, or when you have multiple wave functions, they're going to yield multiple energies. This is where that have the same energy value. This is where you get degeneracy. So this is going to yield the same energy values or degeneracy. Degeneracy. Okay. Cool. And we'll get to the, we're going to build this up a billion times. And we're going to go over this over and over again as we talk about the more and more complicated systems. All right. So particles bound to a sphere. We've got the wave function of theta and phi divided into big theta as a function of theta and big phi as a function of phi. And we've just talked about theta. So let's add phi in here. I'm going to leave theta up. Phi is our exponential. And this is equal to some, again, there's always some normalization constant because now you've normalized the system a couple times. You know that we're always going to carry that normalization constant with us. E to the I m sub L theta. Ooh, that looks familiar. Wink. So there's our particle on a ring. Go team. So that's why we switched over to phi for particle on a ring, because remember, go back to the door. When you're in that corner, phi is what sweeps across this way. So you could really think of that as your particle on a ring. And then when you add the theta component, that's where your particle on a sphere comes in. All right. So an m sub L equals 0, 0 plus or minus 1 plus or minus 2 and so on. Okay. So next, we're going to combine them up. So our azimuthal angle, or sorry, there are colatitude angle wave function, multiply that by our azimuthal angle wave function. And sorry, I'm going to add in more specifics on which ones depend on which quantum numbers. So we've got big theta as a function containing both L and m sub L as a function of theta. Big phi only depends on m sub L, and it's a function of phi. We give this a very special name. When we multiply these two wave functions together, again, these are the angular components of both the colatitude and the azimuthal aspects of where's my electron and what is its energy. And again, R is constant, so I'm not including the radial component yet. I multiplied these two things together and it has a very special term because it's about the spherical aspect. We call this the spherical harmonic. And for my musicians in the room, which I know there are several of you, think about harmonics when you have a string. Well, I'm a cellist, so I'm going to use the string idea. There are certain harmonics where you could barely touch the string and you're going to hit the notes. This is kind of the same idea. There are going to be certain wavelengths associated with the angles here, or sorry, there's going to be certain angles associated with when you're actually going to have constructive interference versus completely destructive interference. And so you've got, this is called the spherical harmonic, and it gives a special notation. It's a big Y, L, m sub L, so L is in the subscript, m sub L is in the superscript, and we say theta and phi are the two things that it depends on, where L is equal to the angular momentum quantum number, and then m sub L is the azimuthal or magnetic quantum number. Okay, go team. So we solve the time-independent Schrodinger equation with the spherical harmonic. We put this into h psi equals e psi using the very large written out with the Laplacian Hamiltonian, like I showed before. And so we do h and then spherical harmonic is equal to E spherical harmonic. And our E that we get from this is equal to quantity, or L times quantity L plus 1 h bar squared over 2I, where I is equal to your moment of inertia. Go team. And L can equal 0, 1, 2, and so on. So notice that L depends, or E depends on the L value. So energy depends on your angular momentum quantum number. But for every angular momentum quantum number, you might have multiple m sub L values. This is where degeneracy comes in, to when you have one p orbital, but that p orbital has an x, px, py, and pz, or px, py, pz. And all three of those p orbitals have the same energy. They are degenerate. This is why. Okay, last but not least, let's plot these suckers. So if I were to plot the spherical harmonic, but I want to plot the square of the spherical harmonic because that's what is my probability density. I don't want to just plot the spherical harmonic by itself because that just gives me the probability amplitude and doesn't tell me much. So I want to plot the square of the spherical harmonic. And if I do that for L equals 0, I get something that looks like a sphere. That's pretty cool. If I do this for L equals 1, I get this kind of shiny looking cool shape. It's pretty neat. I can also get something that kind of looks like this. And if I do L equals 2, I get something that looks like this. Actually, it's a lot thinner at the top. And it's got kind of this roundish thing around it. Go team. And then I've also kind of got this kind of funky donut-like shape. Oops, there's not a convex part there. Anyway, so I get these more and more complicated shapes. And this would actually be, so M sub L equals 0. This is M sub L equals 1. And then I can do M sub L equals 2. And the 2, actually, for this one, for the 2, kind of looks more like that. Okay, there are some great shapes on page, oh, it doesn't show it. Oh. It's going to be in the next section. We'll get to it. Hold on to your seats. But do these look familiar at all? I hope you said yes. We are building towards the atomic orbitals. They are squared wave functions plotted in three-dimensional space. And for a constant r, particle on a sphere, we have the wave function only depending on theta and phi because r is constant, which means we've pulled that into our Hamiltonian, well, part of the eigenfunction, or part of the operator for the eigenfunction equation. We solve the Schrodinger equation, and this is our energy. So those two questions, where is the electron and what is their energy? Well, where is it? Here's the probability density plotted. These shapes are going to start to form depending on our angular momentum and our magnetic angular momentum quantum number values. And then what is it? What is the energy? L times L plus 1, h bar squared over 2i h bar squared, just because that's the quantum of action. And then we've got L and L plus 1. So there's our quantization of our energy states in terms of angular momentum. Cool. Okay, particle on a sphere, check. Next up, we're going to move into actually including the radial component, which will make this a little bit more complicated, but we're going to go ahead and put chemical character to some of these things and actually name the center of this thing a proton and add in the potential energy that a proton would cause. So go team. Email if you have questions. Bye.